Hi, welcome to part 14 of the video series about laws of motion. In the previous video, we have solved some examples related to the friction force. In this video, we are going to solve 3 more questions. Questions we are going to solve in this video are focused more on the theory part of the topic rather than the practical one. Instead of learning how to use the formulas of this topic, we will try to understand when and how to use each formula. In the first question, an object is at rest on a rough surface. A force F is applied on the object with an angle of theta to the horizontal. In the first part of the question, we are asked to find out how the coefficient of friction will change if we increase the angle of theta. As we learned before, coefficient of friction depends on the two materials interacting and has nothing to do with any of the forces experienced by the object. Coefficient of friction may change only if we change the material of the surface or object. That's why increasing or decreasing the angle theta or any other quantity like mass of the object or magnitude of the applied force will have no effect on the value of coefficient of friction. It will remain same. In the second part of the question, we have to find out how the static friction force will change if the angle theta has been increased. Our task has been made easier by the phrase static in the question. But even if it wasn't mentioned, we have to know that if an object is at rest, the friction force applied on it is the static one. Let's remember that the magnitude of the static friction force is equal to the magnitude of the applied force. To find out which force or forces will try to move the object, it's a good idea to start the solution by drawing a free body diagram. Force of gravity is applied downwards. Normal force is acting upwards. In a free body diagram, lengths of arrows are not important, as we draw them even before we start solving the question, and thus, in most cases, we don't know their magnitudes. The third force exerted on the object is the applied force, and the last one is the force of friction. We can split the applied force into its components. F parallel for the one which is parallel to the surface, and F perpendicular for the one which is acting perpendicular to the surface. Don't forget to erase the vector representing the applied force, in case you have drawn its components. As in the exams, you may draw either vector itself or its components. You will be penalized by 1 mark for drawing both on the same diagram. We can see that the friction force is equal to the parallel component of the applied force. The parallel component is in the horizontal direction, and the horizontal line is adjacent to the angle of theta. Thus, F parallel and friction force in this case are equal to F times cosine theta. We know from maths that if you increase the angle, value of function cosine will decrease. As a result, the magnitude of the friction force will also decrease. Unlike the previous question, in this one, the object is in motion. Again, we have to find out how will the value of friction force change if we increase the angle of theta. Everything regarding this question and the previous one are same, except for the state of the object. That's why we can draw the same free body diagram for this question as well. The object is in motion, which means the friction force applied on the object is the kinetic friction force. Unlike the static friction force, we calculate the magnitude of the kinetic friction force by using a fixed formula. Friction force is equal to the product of the coefficient of friction and the normal force. If you forgot how to calculate the normal force for this type of questions, you can click on the link above on the screen. When a force acting with an angle to the horizontal tries to pull an object, the magnitude of the normal force is equal to the difference of force of gravity and perpendicular component of the applied force. Perpendicular component is on a vertical axis and the vertical axis is opposite to theta. Thus, F perpendicular is equal to F times sine theta. As we know, if we increase the angle, the value of function sine increases. Due to the minus in the equation, magnitude of the normal force and friction force decreases. In the last example, the object is on an inclined plane with a rough surface. We have to find out how will the magnitude of friction force change while object is at rest or while it is sliding down if we increase the angle of incline. We have to get used to start solving questions for this topic by drawing a free body diagram. There are three forces acting upon the object. Force of gravity, which we draw downwards, the normal force, which is perpendicular to the surface, and force of friction opposing the motion. As a next step, we resolve the force of gravity into its components, one perpendicular to the surface and another one parallel to the surface. After drawing the components, we can delete the vector representing the force of gravity. Once done with the free body diagram, we can start to look at each case separately. In case 1, the object is at rest, meaning the friction force applied on it is the static friction force. And the magnitude of the static friction force is equal to the magnitude of the force which tries to move it along the surface. In other words, parallel component of the gravitational force. We recall from the previous questions that Fg parallel on an inclined plane is equal to the mass times gravitational acceleration times sine theta. If the angle increases, the value of function sine also increases. Thus, the value of static friction force is also increasing. In case the object is sliding down, the friction force applied on it is the kinetic friction force, which is equal to the product of coefficient of friction and the normal force. On an inclined plane, the magnitude of the normal force is equal to the magnitude of the Fg perpendicular, which can be calculated as mass times gravitational acceleration times cosine theta. If theta increases, value of function cosine decreases, which means the magnitude of the friction force also decreases. Three questions we have solved in this video were a bit complicated ones. If we manage to understand how to solve them, we can solve most of the questions related to the topic of friction force. For now, we have covered CAPS related topics for laws of motion. In the upcoming videos, we are going to solve some more questions to deepen our understanding of the topic. Don't forget to subscribe and turn on the notifications in order to be updated about my new videos.